Episode 8. Today, we're going to build our own sentence embedding model. We start with importing our numpers, our pandas. We import UMAP, the dimensionality reduction algorithm, HTTP scan, our clustering algorithms, prettyprint, and of course the sentence transformers. Then I load my sentences. Again, the document is the Deloitte's Tech Trend 2021, and I already downloaded all the sentences to this text file. Just to make sure, the length of the sentences should be 1775 sentences, and make sure to check the sentences. Okay, these are the sentences we're looking for. Since we have within BERT a maximum input sequence length of about 128, make sure that your sentences are not longer than that. And remember, BERT is a word piece model. Therefore, if we check how many words we have in a sentence, we can clearly see that in all the sentences of the document, we have here one sentence with about 45 words. This is the maximum amount of words within one sentence within our document. And if you want to find this particular sentence with exactly 45 words, you can go and check if it's really this sentence, and if not, a comma has been misplaced or maybe some exceptional mark has been put within the sentence. Now, in the other episodes, I showed you how to apply BERT sentence transformers, and download the pre-trained sentence transformers from SBERT. But today we're going to build our own system, our own model. And for this, we have a short look of the graphic, how we're going to build our first trivial model. And of course, we start with our sentences. We feed the input sentence into a transformer network like BERT. BERT itself produces contextual word embeddings for all the input tokens in our sentence. And you remember, BERT is a word piece model. So the vocabulary strength of BERT is about 30,000 pieces of vocabulary, not all of them words. And if your words in your text are not within the vocabulary, BERT simply does some deconstruction of the words. It breaks it down to word pieces, which can even go down even to single characters of the words. Then, as we want a fixed site output presentation, let's say the vector u of our sentence, we want to have for each sentence a high dimensional vector, we need a pooling layer. Now, the methodology for pooling can be quite challenging, but here in our simplest case, we go with mean pooling. And then we come up with the result, a simple vector in 768 dimension, or for BERT large in 1024 dimensional, creating a feature space and a coordinate set for our particular sentence. And we have 1775 sentences within our document. And this is what we're going to code right now. So we design our own sentence embedding model. Here I would like to show you, wait a second, the homepage of SBERT, the API. There are 3 basic steps. Let's start from scratch. We are operating in PyTorch, of course. We have a transformer model, and this transformer model we can download from Hugging Face. Currently, there are more than 6,000 models on Hugging Face. You just go there, you download your particular model, and you check it out. Let's do it. I'm gonna show you. So you see already here we have about 6,718 models currently in Hugging Face, and the first model, great, and you see 15,000 downloads already, base uncased, and here the distilled version of BERT. If you go within this model, you find a short model card. You can find out what is it, where it has been trained, what's the methodology of it, and you see the download number, 1.9 million downloads last month. So you choose your particular model, and we start with the most downloaded model. It's a small but beautiful model, and we choose this model. So what you do, you simply insert this model here. Since it's absolutely compatible with SBERT, our sentence embedding model, you define here the maximum sequence length, the input length. And since we have about 45 words in our longest sentence, and let's say that not all the words are within the vocabulary, and BERT will perform some word piece operations on these sentences. Just to be on the safe side, we go with 256 as the maximum sequence length. Next step, as I already showed you, after we have applied BERT, is the pooling layer. Now for the pooling, it is quite easy. You have now your word embedding model, and you just get the word embedding dimension, and you do the pooling. We will have a look at it in detail in episode 9, where I show you how to fine-tune the parameter. And last step, you can have here now a dimensionality reduction already here within our sentence embedding model. You can say that you apply another layer, that's not depicted here, a dense layer, with a certain activation function, and we choose here the Dungan's hyperbolicus. You can reduce the output features. Remember that this still Roberto, I have Roberto base, operates in, I think, 768 dimensions. And now we reduce our output to 256 coordinate sets modules. And then you put it all together. You have your sentence transformer, and you have the models word embedding model. This is the first one, the pooling model, the second one, and the dense model to reduce the dimensionality. And this is it. Now you have an operational model. So let's perform this operation. And since I already downloaded the Still Roberto base, this should be done in no time. Come on. 1, 2, 3, 11 seconds. Yeah, just want to let you know this is done on a CPU-only machine, as a home PC. I have no NVIDIA graphics card, no CUDA core acceleration, and you can do it the same. You can perform these models on your home PC, no problem at all. So if you're interested in the model itself, it is very easy to check out which model have we now built together. So of course, sentence transformer, this is the envelope shell that we have, and then we have the transformer. And here we have chosen the Roberto model, and just to have a very simple look at it, that you see the different layers, the different transformers, and you see, for example, we have a dimensionality of 768. And now here, this is the model, and now here we have the Roberto layer 0, and then I think we have 6 layers. Let's have a look at it. We have 6 Roberto layers, 0 to 5. Then, of course, we have here an output layer, and we have feature in, output feature 768 dimensional. We decided here, another pooling layer. We have another 768 dimension. Then we constructed the pooling layer, and then we have a dense layer with the activation function Tangens hyperbolicus. And this transforms our input feature from 768 dimensional space to a 256 dimensional space. It's a topological space, of course. And just to be on the right side, we check again the maximum sequence length of the model is 256, which we decided as an input sequence. Now, those 3 commands here, I would highly recommend to you to have a look at the API from SBERT and have a look in detail of the class definition. Here we have the first command, it's the transformer command, and you see the parameters. At first, as I already shown you, the Hugging Face model name. This is easy, you go to Hugging Face, as I showed you, you choose a model, you insert your model. The maximum sequence length, we have decided 256. Then you can pass arguments. You can decide some cache operation, add some tokens, and of course, if you want, do some lowercase. The second command in detail here, the class pooling. The pooling takes the following parameters: the word embedding dimension, the CLS token, remember BERT, CLS token, the max token, the mean tokens, the mean square root of the length token, and default, as you can see here, and this will be of importance, the pooling mode, yeah, would be nice. The pooling mode, heaven's sake, is mean. The mean of the tokens is true, is activated by default. And then, of course, you have a dense layer, the in features, the out features, a bias activation function, and you can set some initial value for the matrix of the weights and the bias. Further classes allow you to perform further operation if you have some asymmetric model, but later more about this. So this is our model. And now let's encode this model. We have all our sentences. We have defined a model. So let's apply it. And you see the command is relatively simple. I've chosen a batch size of 128, converted to a NumPy. We're operating in PyTorch, and I want to show the progress bar. This should take on my little CPU, and I think you should be able to have an insert at the top of your screen where I show you my CPU and my memory parameters. And as you can see, I have a 6-core 12-thread CPU from AMD, and it's running about 60% on all 12 threads. And regarding the internal RAM memory, it is hardly 8 GB of RAM. It's done in 38.7 seconds. We check the output, and the sentences are still the sentences. The embedding is an NumPy ND array, as it should be. We have 1,775 sentences, rows, the columns, the dimensionality is 256. And for the sentences, we're going to merge it together is again 1,775. That's perfect. I would recommend to you have a look at the embeddings, how they look. And this should be a 256 dimensional array for each sentence. Yes, it looks about right. This is it. Next step is now to reduce the dimensionality. And a highly successful algorithm I would recommend to you and I use regularly is UMAP. It's a uniform manifold approximation and projection. Finding a low-dimensional embedding of the data that approximates an underlying manifold. It is not a trivial algorithm. It takes a lot of insight from algebraic topology, from mathematics, and some genius encoded all the different steps and put up a GitHub repository. So we are now in the favorable situation to just download UMAP, define 2 parameters, and say go. 2 important parameters here. At first, the number of components. This means the dimension. We have 256 dimensional topological space, and we want to reduce it to 12 dimension. And since the background of UMAP constructs some topological open cover with a different, more or less it's an Euclidean space that has a different metric, and the metric of all points are not compatible. But anyway, there's no distance function, there's no Euclidean metric available. Therefore, we have to define something where we say, okay, if you take the 5 nearest neighbor, they should form, or within this enclosure, within this algebraic cover, it should be regarded as connected on the manifold. But please refer to the official documentation, UMAP. It is gorgeous, and you see here that the class of UMAP has quite some parameters to adjust to, and I will show you a little bit later on what are my specific parameters, as you can already see here. So we have done the calculation now. It took about 37 seconds, and we reduced all our embeddings down from 256 dimension to about 12 dimension. And now we have for each and every sentence an NP array where we have exactly 12 coordinate pairs of the vector for each sentence. You can save it now, you can transfer it to Colab for further calculation on a GPU accelerated system, but we stay here on our CPU only PC, and we perform now a clustering algorithms. And with UMAP, there's a beautiful hierarchical density-based spatial clustering with some noise, and this is important. I'm going to show you in a second why. And the API is beautiful. And we start this algorithm. Complicated, but it's also beautiful. There are two main parameters you should adjust. First is the minimum cluster size, clear, and a minimum sample size. The larger values of minimum samples will provide more conservative the clusters. More points will be declared as noise. This means the higher the number, the sharper the algorithm, the higher the amount of sentences the system regards as noise and not belonging to a specific active cluster. You can choose to check out different metric within this space, and just to be here complete, you have here the different metric that have been implemented within this algorithm. I'm going to choose an Euclidean metric, and of course the cluster methodology. I choose not excess of mass, but leaf. The leaf size is 40, and I apply it to my 12-dimensional UMAP embeddings. And if we do this, we end up with a cluster distribution that is quite interesting, because we have now 8 clusters. And from our 1775 sentences, the system regards 821 sentences as noise. Cluster -1 is system inherent declared as noise and does not belong to any of the other operational clusters. Cluster number 2 with 227 sentences is our biggest cluster, and since we decided that the minimum cluster size is 60, we have here cluster number 6 with 73 sentences. If you have more than 15 clusters, you can have a look at the tail of the Panda data frame and check out, of course, the definition of the cluster calculation. Again, we have leaf, we have the number of jobs is 1, so all threads. The minimum cluster size is 60, the minimum sample size is 20. Now what we have? We have a vector, a sentence embedding vector for each and every sentence, and we have it clustered, and the vector we have an algorithm to reduce the dimensionality of this vector. Now we apply again UMAP to break it down to 3 dimension, because we want a visualization of all the sentences within the document, and we want to see how the sentences cluster. You could also ask, what are the main topics of the document? What are the main highlights about what topic are all the sentences configured? And it is a point why I would regard it as a data topology question, which we will program, we will encode, and we will have a first look. We now put together in a data frame the sentences, the cluster labels, and the X, Y, and Z coordinate for each and every sentence. And to check that we have the correct amount of clusters, cluster 8. Now, since we have now all the sentences, and the sentences can be quite long, we want to apply another idea that has been encoded by 2 people, Martin Grotendorst and Dima Angelov. Here's the reference to the articles. Have a look at them. They're really interesting. We're going to have a look at the word in each cluster, but not just the words, but also the bigrams and the trigrams of each cluster. It's easy to achieve because we activate our count vectorizer. And from the n-gram range, we have here 2 stands for bigrams to 3 trigrams. So I want to have all the bigrams and trigrams that are available in my document to be depicted. And we end up with something like this. It's a data frame. It shows us cluster -1, cluster label -1 is the cluster which are regarded as noise. The magnitude is the amount of sentences, 821 sentences within this cluster, which has not been allocated to any other active cluster. And now the top 10 words of all the sentences within this cluster are zero trust, machine learning, decision making, supply chain, low code, data scientist, human experience, and supply chains, plural. As you can see, the top word now within all the sentences in a cluster are presented to us, and we get a better overview of the content of the cluster. Now what we do is we merge it together. We make a little bit nicer presentation. What we also can do, we can apply this bigram logic to the whole document, all clusters included. And it's a kind of check if our algorithm works well within the document. And here we have the result. If you apply it to all clusters, the first trigram, and I just look here at the trigrams, model, development, and deployment. This sounds about right, given the title of the document, Artificial Intelligence, Tech Trends 2021, and the application for business. New ways of working, of course, COVID, technology tools that support certain change. Interesting here is this diagram that tells us about the time scale that is most mentioned within the document, months. So consultant paper referred to month as a time scale instead of years. Subject, of course, legacy core systems. You have to transform the supply chain, the business base, your core of the business, the modernization within the business. And here we go on. So we can say that given that those are the most important trigrams of the whole document, I think our clustering is pretty good. But of course, let's have a look in detail. We do some network X analysis and then we just plot it in Plotly. These are all our sentences, and just to be complete, we also provide here the legend. And what we can see here now is a three-dimensional visualization of all the sentences within our document. We have color-coded the cluster that we identified, 0 to 6, 7 clusters, and the cluster, if you want, with the noise. This is the cluster here with the light gray points. This is the noise. But you see here all sentences, and as you can see from the distribution of the cluster found by the algorithm, this is quite actually good. It looks really interesting because all the dense region of our graph have been identified to contain at least one cluster and the interlink. And you see here there's a region where there has no cluster been detected. And if you optimize the clustering parameter, you can even extend your cluster size or maybe identify a cluster here also. So this looks quite interesting. This is what we expected. The algorithm works. Our sentence embedder model based on BERT transformers performed reasonably well. We would not see any major problem right now. And the next step is to optimize the performance of this model. Thank you.